Welcome to Kushar Academy, Unleashing Potential. Today we will be studying about center of gravity and uniform circular motion. And apart from this, centripetal force and centrifugal force, which is part of uniform circular motion. So, about center of gravity. What is center of gravity? Center of gravity of a body is the point about which the algebraic sum of the moments of weight of the particles constituting the body is zero, and the entire weight of the body is considered to act at this point. So this looks complicated, but we can see here algebraic sum of the moment. Let's see this as a body. Okay, so consider that this body is having these weights. This will be distributed throughout the body, but for simplicity we are considering that this body has only these weights. Now, so center of gravity is a point here G about which all the moments of the weight of the particle is zero. About this point, what is the moment of weight of the particle at this point? So it is force, that means this weight, into the perpendicular distance from the axis of rotation, means the center of gravity. So the perpendicular distance will be this much. And what is the tendency of rotation? It is this way, that is anti-clockwise. All these particles on the left of this line will be having a tendency of rotation towards left. See this one. This also will be pushing the body, rotating the body towards left. And what is the distance? This is R1. So in this way, we'll be calculating all these weights and the movements of these weights about this point G. Similarly, if we see on the right hand side of this, what will the moment of this weight? It will be force, that is the weight, and this distance, say R. Similarly, for this, it will be this perpendicular distance into, say, R2. For this, it will be R3. And what is the tendency of rotation? It is clockwise. So again, we'll go into the definition. What it says is a point about which the algebraic sum of the moments of the weight of the particle constituting the body is zero. So what we have seen, we can add all the moments, the clockwise moment and the anti-clockwise moment, and at the point G, these moments will be zero. G can be, we can consider any one point, for example, here. But if we take this point, say P, and if you calculate the moments, it won't come as zero. So we'll check it out where it comes at zero. And if the G is that center of gravity, then the sum of the moments will be zero. All sum of the clockwise moment will be equal to all the sum of the anti-clockwise moment. This position depends on the shape of the body or the distribution of the mass of the body. We are now able to see that if the weights are different or the distribution of mass is different, the center of gravity will be different. For example, if we add one more particle on this body, then this moment towards clockwise will be extra and this won't add to zeros. All clockwise and all anti-clockwise won't be equal. So this G will have to shift, say, somewhat here. So the new center of gravity will be shifted little towards right, so that all the sum of the clockwise moment and all the sum of the anti-clockwise moments comes to zero. Important point to note here is the position of the center of gravity of the body depends on its shape or distribution of mass, and it is always not necessary that the center of the gravity will lie within the material of the body. For example, if you consider one shape, let's consider a shape, suppose, which is like this. So intuitively, we can see that the center of gravity should be somewhere like this, which is not lying on the body. That means there is no point in the body itself, be it here, be it here, or be it here, where some of the movements will come to zero. Center of gravity can also be understood by the balance point. A solid can be balanced by supporting it at its center of gravity. Why it can be balanced? Because at the center of gravity, the sum of the clockwise moment will be equal to the sum of the anti-clockwise moment. Since the net moment is zero, there has to be no rotation. Hence, by our definition, what we have seen, that that point has to be center of gravity. Like for example here, if you are able to stable it here, that means the center of gravity is at this point. What it means that if it's the mass on this side is more because iron is more, and the mass of this side is less because it is made up of plastic handle. So some of the moments anti-clockwise from this point, axis of rotation, and from this point the clockwise rotation is zero. Hence we can balance it out at our fingertip. So it is because the algebraic sum of the moments of the weight of this hammer is it is because the algebraic sum of the moments of the weight of all the particles on this hammer is zero. Clockwise equals to anti-clockwise. Recall that this was the case of the equilibrium as well. Center of gravity can be done for many other particles also. Like if you see that if you consider this to be as Earth and this to be as Moon, and if it is rotating, because we know that both are rotating as well as revolving, so center of mass shifts due to the motion because the distribution of weight is different. Similarly, on the right hand side also we can see that the center of gravity shifts. Here it is at this point, and in another point it is somewhere else. So sometimes it is on the earth, sometimes it is outside the body also. Let's see the center of gravity of some regular objects. If an object is a rod, which is a regular object, it has to be the midpoint of the rod, because at a midpoint we can balance the rod. Circular disc, it has to be at the center of the circular disc. Sphere, you can imagine likewise here. See, in a circular ring, it is at the center disc at the center. In a triangular lamina, equilateral triangle, it will be the centroid. In a rectangle, it will be the intersection of the diagonals, and if we put a finger here, we can balance this rectangle. That means equilibrium is there. That means the sum of the anti-clockwise moment and sum of the clockwise moment are equal. That's why it is in equilibrium for parallelogram. So we have to imagine of putting our fingers at any point, and when it doesn't rotate, that point has to be the center of gravity. Clear? How to find the center of gravity of an irregular object? Whatever we have seen earlier was for regular object. It was easier by pointing a finger and stabilizing it, or by imagining that it is. But what happens if the weight distribution is not even, or if the shape of an object is irregular? How to find that? We can find the center of gravity by a method which is known as plumb line method. We have to have some steps how to find it out. To find for irregular objects, what we do, that we make 3 holes in that object. See, hole number 1, hole number 2, hole number 3. What we'll do, that we will balance this shape by help of some say nail or something, and we'll see when it comes to stability. Say this is the shape that it takes when it becomes stable. That means when it doesn't rotate, it stops rotating. Put a straight line here, draw a straight line here. Similarly, then again we'll do the same procedure with the hole number 2, and we will draw a line here perpendicular to the ground. Similarly with the line 3. Now we have drawn the line 1, line 2 and line 3. What we observe, that all these lines intersect at a common point. The point of intersection is the center of gravity. So what are the steps that we take? We take 3 fine holes, freely suspend from hole 1 first. When the lamina comes to rest, draw a straight line along the plumb. Repeat it with hole 2 and hole 3. Here also we can see that it is freely suspended at this point. We draw a line, then we take another hole, Then again we freely suspend, and when it comes to rest, we draw a line, and this point of intersection will be the center of gravity.
The centre of mass of an object is the point where the entire weight of the object appears to act. Working out the centre of mass of a symmetrical object is easy. It's simply where the lines of symmetry cross. However, it's very unlikely that you'll be dealing with such perfect shapes, so you work it out by suspending the object freely along with a plumb line. The centre of mass is always below the point of suspension, so by marking the vertical along the plumb line, you know that the centre of mass is somewhere along that line. By suspending the object from another point and repeating the process, you get two lines that intersect, and the point of intersection is the centre of mass. The position of the centre of mass is very important when it comes to the stability of an object. For example, a double-decker bus is built to have a very low centre of mass and a wide base, so that the line of action of its weight stays within the base when it goes around a sharp corner. If something has a high centre of mass combined with a small base, then it's very unstable and will topple over with minimal effort.
Now we are moving to another topic, which is uniform circular motion. What is a uniform circular motion? When a particle moves with a constant speed in a circular path, its motion is said to be uniform circular motion. Just like look at here at the arrow, it is moving at a constant speed in a circular path, so we can very well say that this is a uniform circular motion. Now the direction of circular motion. If we look here, we see that the direction is constantly changing. The arrow, the green arrow, shows the direction. So, when a particle moves with a constant speed in a circular path, its motion is said to be uniform circular motion. At any point, the direction of motion is along the tangent drawn at that point of the circle. Just like here, the tangent drawn perpendicular to the center is the path is the direction of the speed at that point on the circle. It's constantly changing. Just like we can see at top, it is towards left, at C it is vertically downwards, at D it's towards right, and at A it is said to be vertically upwards. Circular motion has acceleration. Now what is so? We are saying that the speed is uniform, but velocity, being a vector quantity, depends on direction as well. If the speed is constant but the direction is changing, that means velocity is changing. If you remember correctly, the Newton's first law, it will say that a velocity is constant if there is no external force. But here the velocity magnitude is constant, but the direction is changing, that means velocity is changing. If a velocity is changing, that means there has to be an external force. And if there is an external force, there has to be an acceleration. That's why circular motion is said to have acceleration. Uniform circular motion versus uniform linear motion. Linear motion means a motion in a straight line. Uniform linear motion. Now, in uniform linear motion means since the body is moving in a straight line, so speed and velocity magnitudes are constant. Whatever is the velocity's magnitude, that is also speed's magnitude or value of the speed. Acceleration is zero because the velocity is not changing its direction. That's why acceleration is zero from Newton's first law of motion. Uniform circular motion. Speed is constant. Velocity is variable because the direction is constantly changing, and since velocity is changing, force is there, and if force is there, acceleration is present. So these are the differences between uniform circular motion and uniform linear motion. Now we have already discussed for a body to move in a circular motion, it is accelerating, and if it's accelerating, there has to be a force attached to it. So what is the force? The force which makes an object move in a circular path is known as centripetal force. What are the examples? Some of the examples of the centripetal force. In an atom, electron is moving around the nucleus due to which force? Electrostatic force of attraction towards the center. Similarly, planet moves around the sun due to gravitational attraction. Moon revolves around the earth due to gravitational attraction. Similarly, if you see here, if you are revolving a bucket tied with a string, so it is similar to stone tied at the end of the string and whirled in a circular path due to the tension force in the string. Then there is a concept of centrifugal force. Centrifugal force is a force acting on the body away from the center of the circular path. Its direction is opposite to that of the centripetal force because centripetal force direction is towards the center and centrifugal force direction is away from the center. Magnitude is same as centripetal force, and centrifugal force is not a reaction force. It's not a reaction to centripetal force. It's a imaginary force. It's not a real force. We'll study more about it in the next slide. Before we understand what is an imaginary force, we have to understand what are inertial and non-inertial frame of references. For example, a train is accelerating with an acceleration a and a pendulum is here. So if the train is not accelerating, the pendulum would have had been in this position. But since train is accelerating, we can imagine that it will be shifted in a left hand direction. So this is the actual position of the pendulum. Now, if I'm standing outside this train, what will I observe? That this ball is also accelerating. But suppose if I'm standing inside the train, what will I say? This pendulum is not moving, it is stationary here. So why this change of thing happens? It happens because we are looking at the same thing from different perspective, one from the ground and one from the train. If you see here, why it is stationary, that means total force on it should be zero. For the girl, it is accelerating as ma, force is ma, and hence it is moving. But for this person who is inside the train, it is, if ma would have been here, then the ball would have been accelerating in this direction. But since it is stationary, an equal force is said to be acting on the left hand side, which is equal in magnitude to the ma, and we say a force ma is acting on the left, hence these two forces cancel out each other, hence there is a no motion in the pendulum. Now this is not a real force, this is an imaginary force which we have added to make it consistent with Newton's second law, that force has to produce an acceleration. This force we say to be imaginary in nature because we have added it ourselves. And why do we have to add it? Because of the change of reference or the change of frame. Earth is said to have be in inertial frame, and if anything which is accelerating with respect to Earth, and if we are observing from that reference, we have to add a imaginary force so that all the Newton laws are obeyed in this frame of reference. Now coming to centrifugal force. If we see this object, it is similar to what we have seen in the train. Now this is rotating here, this boy is rotating here, and if we are observing from outside, this boy is moving in a circular motion due to a centripetal force in the inward direction. And the log is also there, and if a boy observes the log, it says, the boy will say that the log is not moving with respect to me because the boy is in a non-inertial frame of reference, that means a rotating frame of reference. So a pseudo force is added outwards so that the motion of the log is zero, similarly to what we have seen in the earlier slide. This fictitious force is known as centrifugal force. Once again, to recap, what we observe from ground, centripetal force provides the circular motion. Observation of the boy who is inside this circulatory motion. Boy sees the log is to be stationary. What are the forces that he will see? One is the centripetal force towards the center, and one is the imaginary force outwards the center, the log to be stationary. So the conclusion that we get that centrifugal force is not a real force. It's a fictitious force. Only force involved actually is the centripetal force. Just when we are changing to another frame of reference, we are adding that imaginary force. So centrifugal force is applied when a non-inertial frame of reference is used. So this brings us to the end of chapter 1, in which we had studied center of gravity and uniform circular motion. Thank you.